All right, class, so this is an explanation video for these three different integrated rate law problems from chapter 13. These are just a selection of integrated rate law problems and then an activation energy problem, so another problem that we haven't really spent that much time on, but I would encourage you to sort of go over. So this is the sheet with all three. I'm going to go through each one individually in this video, so if you want to skip around and find a specific problem, definitely do that. But we're going to start at the top and sort of work our way through. So this is our first one, 13.26. This is a integrated rate law problem. So the way that I'm sort of recognizing that, it says that the thermal decomposition of phosphine shown below, so this is my chemical reaction, is first order. So I'm told that it is a first order reaction. And we're told what the half-life is. So this would be the T1 half is 35 seconds. So for A, it says calculate the first order rate constant for the reaction. So when I'm looking at a problem like this, what I might think of is my equation sheet. So on my equation sheet over here, I've got my integrated rate laws, so zero order, first order, second order. I'm told that this is first order, so I'm going to be using this equation here. We could also use our half-life equations, but we don't have those for our final exam. So if we just write out the first order rate law equation, natural log of A at time t, is equal to the natural log of A initially, and this is going to be minus KT. So again, this equation here, I'm just reading that off of my integrated rate law, so this is my reaction, or my equation right there, and just copying that down. Now, the special thing that we need to keep in mind for a first order reaction, the half-life is constant. So if you look at the half-life equations that we looked at previously, this is sort of just almost a piece of trivia that for a first order reaction, the half-life is constant. And so it really doesn't matter what our initial concentrations are, the half-life that we're going to observe is always going to be the same. So for this problem, this reaction, for calculating the first order rate constant for this reaction, we're told what the half-life time is, and then these initial concentrations and concentration at time t, it really doesn't matter what we choose. So I might just go ahead and choose the natural log of 1 equals the natural log of 2. So if this is my initial concentration, half of that is going to be 2, minus k, which is what we're looking for, times t, which is 35 seconds. So this would be my equation. And if you solve this for k, so just sort of move, do the calculation, you end up with a k value equal to 0.0198 seconds to the minus 1. So that is my answer for A. That's my first order rate constant. And again, the numbers that I've plugged in here, I arbitrarily chose 1 and 2 because I wanted to have a half of my initial. So it seems easy to choose 1 and 2. You could use 0.5 and 1. Really, whatever you choose, it should calculate out to the same k value. So I might encourage you to try that. Try some different numbers in there and see if you end up with the same k value. You should, because for a first order reaction, the half-life is constant. Once we know that k value, we can do this next part for B. And this says calculate the time required for 95% of the phosphine to decompose. And again, in this case, it really doesn't matter what we necessarily plug in here for our concentrations, as long as we've got 5% left over of what our initial was. So the easiest way for me to do this, calculate the time required for 95% of the phosphine to decompose. That means that there's only 5% left over. So 5% of 1 is 0.05. So this would represent a time after only 5% is remaining, or 95% of this 1 has gone away. And again, any numbers you choose, as long as they're 95% right gone, it doesn't really matter. So this would be minus k, which we now know is 0.0198 times t, and that's what we're solving for, that t. And if we solve this for t, we get 151.3 seconds. So that is my answer for the amount of time required for 95% of the phosphine to decompose. So sort of two-step problem here, and a pretty classic sort of problem like this. Let's do one more, or I guess two more. So this one, 13.27, the rate constant for the following second order, so now we're sort of going to be in the second order realm, is given to us here. So that is our k value. And we are given our chemical reaction, starting with the concentration. This would be our initial concentration. Calculate the concentration after 22 seconds. So again, here we're thinking, okay, this is a second order problem, so I'm going to be using the second integrated rate law, second order integrated rate law. So let's go ahead and write that down. Try to stay organized here. So for my second order, it's going to be 1 over a at time t is equal to 1 over a initially. Oops, this should be initially. And then plus kt. So sorry about that. This is my initial concentration. Again, I'm just reading that off of my second order rate law here, a at time t, a initially. So for this one, I basically have all the information that I need to solve for part A. So part A, we're having an initial concentration of 0.086, and we're asked to calculate the concentration after that certain amount of time. So I might write 1 over A is equal to 1 over 0.086 plus K value, which we're given, 0.80 in this case, times T, so 22 seconds. Now one thing I do want to just double check is my units here. So my units on this K value, molarity and seconds inverse, and then this is going to be seconds. So seconds and seconds consistent, that is good. Now I'm going to go ahead and solve for this concentration of A. So do a little bit of algebra here. I would sort of just get a value for this and then take the inverse of that to solve for A. And my A concentration should be 0.034 molar. So that's the concentration after 22 seconds has elapsed, has gone by. For B, it says calculate the half-lives when I've got two different starting concentrations. Now, since this is a second order problem, the half-lives are going to be different based off of how much concentration you start with. In first order, like we saw in the first problem, it's going to be the same. Every half-life is going to be the same. But for a second order problem, it's going to be different. It's going to be a different half-life depending on how much we start with. So if I'm looking for T1/2 when the concentration of NOBr initially is 0.072, the concentration at T1/2 of NOBr T1/2 should be half of that, 0.036. And that's what I'm going to plug in to my equation. So it would be 1 over, make sure you guys can see, 0.036 equals 1 over 0.072 plus 0.80 times t, and that's what we're going to be looking for, is that time t. Solve this for t, you get a value of 17.4 seconds. So that would be the T1/2, the half-life of this reaction when the initial concentration is 0.072. We can do the same thing essentially for my other condition here when my initial concentration is 0.054. So NOBr initial equals 0.054. Concentration of NOBr at T1/2 is going to be half of that. So just take half of that is 0.027. And then I can do the same sort of calculation. 1 over 0.027 equals 1 over 0.054 plus 0.80 times t. Solve for t, and you should get 23.1 seconds. So again, a little bit messy here, sorry about that. This is the 0.80, that is my K value, and I'm just solving for T here. So that would be my half-life. Okay, one more. Hopefully we've got enough time. So on this last one, we're asked to, you know what, I'm gonna make another video for this one. So for 13.42, we're gonna do a different video, so just look for that. All right.